tall straw. Limit to the tallest straw that you could possibly drink out of. Suppose you trained at this and were able to make your chest even stronger, to apply greater forces and create lower pressures inside your lung, mouth, straw cavity. How high could you get the water to rise, relying on the outside air pressure of 1 atmosphere to push down on it and force it upwards? Is there a limit to the height that you can pump, we would say suck, water using atmospheric pressure, using 1 ATM? So what if you were able to reduce the air pressure in here all the way down to 0? What if you could create a vacuum inside your straw, mouth, lung cavity? That brings us to example 5 and the concept of a barometer. So let's look at exactly that. What if you had a very tall straw with 0 air pressure inside this cavity here, a vacuum inside that space? Here's our very tall straw, and how tall would it be? There is a vacuum up above, so 0 air pressure. That means then, let's see, the pressure difference between the top and bottom of this column would be 1 full atmosphere. That is 1 atmosphere on the outside versus 0 atmospheres here in this vacuum. So with that pressure difference equal to rho GD for the depth of this column of water, set that pressure at max height to 0, and we can solve for the depth of this column. Doing so then is going to produce 10 meters. We could get at most a 10 meter high column of water, relying exclusively on an outside air pressure of 1 atmosphere to push down and then push up on that water. What that would mean here is that a 10 meter tall column of water here would have the same weight as the entire column of atmosphere going up to space. And 1 ATM down here at this base level could support both of those columns, the water and that atmosphere. So we could use a device like this to measure changes in the outside air pressure. It's normally about 1 ATM, but that varies from place to place and from day to day. So this could be the basis for an air pressure measuring device. That's what a barometer is, an air pressure measuring device. However, remember our scale, this is in meters. So your water column based air pressure measuring device would have to be, some 10 meters tall. That's completely impractical. Nevertheless, if you were to build a 10 meter tall column and look at fluctuations in the height of the column as the outside air pressure fluctuated over time, then we might be able to notice on a weather map like this, high pressure and low pressure regions in weather systems. So in this map of the US, when you see a high pressure zone, that means a region where the air pressure is slightly above the average of 1 ATM, maybe as much as 1.01 ATM in a very high pressure system here or over here. So in this picture with these little red arrows, I've drawn the net force that would be exerted on a little parcel of air, a little fluid element that was bordering between the high pressure and average pressure zones. So this high pressure zone is going to be exerting net pressure forces outwards on all the sort of bordering fluid elements, causing accelerations outwards that'll be affecting the total movement of this air mass. Down here in this low pressure zone, that might mean a mass of air whose pressure was a little bit below atmospheric pressure, maybe 0.99 atmospheres in the extremely low pressure system there. So here the net pressure force on fluid elements bordering that system would be inward, causing accelerations in towards this low pressure region here. And we could be making these measurements with a very tall column of water like this. We call the air pressure, the outside air pressure, the barometric pressure. So on a very high pressure day, if the outside air pressure went up to 1.1 ATMs, this never happens on Earth naturally, but if it did, that would push our column of water upwards from a normal 10 meters all the way up to 11 meters high. Or if we saw that column drop down to 9 meters, that would mean that the barometric pressure was an extremely low 0.9 atmospheres. This also never happens on Earth naturally. But by monitoring then the height of our column of water, we are measuring the outside air pressure. All right, but no one's going to build a 10-meter tall instrument. We need a denser liquid. And that's where mercury comes in. How tall would a column filled with mercury need to be to function as an effective barometer? Mercury, remember, is about 10 times more dense than water. Specifically, it's about 13.6 times the density of water. So if this is our column full of liquid metal, that mercury here, 1 atmosphere of outside pressure, and then a vacuum up here in this section, then that pressure could push up mercury how high? Note we've got a different scale here on this diagram. We're in centimeters this time. So, okay, the pressure difference between 0 and 1 atmosphere at the top and bottom of that column, set that pressure difference equal to rho GD for the depth of that column, solve for the depth of that column. And this time we'll use more precise values, an outside atmospheric pressure of a standard 1.013 times 10 to the 5th pascals. The density of mercury, 13.6 times the density of water. And little g, we'll use a more specific 9.8 newtons per kilogram. And if we do that, we'll get a result of 760 millimeters, or about 76 centimeters. That would be the height of this column of mercury. That's less than a meter. That you could build and use in a laboratory or a weather measuring station. So a mercury barometer is a practical device for measuring air pressure. In inches, that'd be about 30 inches tall here. Another name for this unit is torr, because this device was invented by none other than Torricelli in about 1643. This guy, the inventor of the mercury barometer, was believed to be the first person to actually create a vacuum in laboratory by building such a barometer as this. Torricelli is also famous for having the strangest mustache I've ever seen.